Hello, today we're going to talk about concentration changes over time. So here's a graph that shows the different orders of reaction and how their concentration versus time graph looks. So in a zero order reaction, the concentration versus time graph is a straight line with a negative slope. And this is for the concentration of a reactant. Now, for first order, that's the red line here. You can see that it decreases, but it slows down the increase as time goes on. Same idea with second order, but it looks a little different. It has a different pattern of decrease. That's the yellow line here. Right. So the only one that we can actually get really useful information from just a basic time versus concentration graph is that zero order reaction. If that's a straight line, we know it's zero order, and we can get some useful data from that. So for a zero order reaction, we can get a lot of information just from a concentration versus time graph. The concentration of whatever reactant over time. So that graph is going to look like a line with a negative slope. And the slope of that line will be equal to the negative rate constant K. We also know that the y-intercept here is going to be equal to the initial concentration. We use A sub 0 because the time is 0. So the concentration at time 0 is the initial concentration. Now, if I'm going to write an equation for that line, I can use y equals mx plus b format, where y is our concentration. Our slope is negative k, our x is the time t, and then our y-intercept is our initial concentration, A sub 0. Sometimes people will put a t on that, so we can notice that the concentration of A at any given time is equal to the negative rate constant times that time t plus your initial concentration. So we can use this equation to help us find information about the change over time, or we can use the graph itself of that line to find the information. And don't forget that the units for K, when it's zero order, is just the concentration unit and the inverse time unit. Now, first order, if you remember, had that changing slope over time. So what we can do is if we take the natural logarithm of the concentrations, and plot that versus time t, then we will get a straight line graph. Chemists really like straight line graphs. It gives us a lot easier to use information. So first order, the straight line graph will be natural log of the concentrations versus time. The slope is still negative k, which is nice. The initial concentration is the natural log of the y-intercept is the natural log of the initial concentration. Don't forget that the units for k is just your inverse time unit. And then if I'm going to write an equation for that line in y equals mx plus b format, our y values are the natural log of the a at whatever time t. Our slope is negative k. X is just the time unit, or the time. And then our y-intercept is the natural log of a sub 0, or a initial concentration, a. And again, this is called the integrated rate law. It helps us track the change over time. Or you can get the information from the graph itself. But yeah, first order, this is what the decay looks like. Now, you should know that some reactions are first order, but also nuclear decay follows first order kinetics. So if you have like a radioactive substance, it will decay following first order kinetics. So the last one that you guys need to know is second order. And if you remember, second order also changes slope over time when we're plotting just concentration versus time. But it changes differently than first order. So if I want to find a straight line graph for a second order reaction, I need to plot the inverse concentration compared to time, okay? And it will give a positive slope. It's the only one with a positive slope. So the slope is equal to k, not negative k, because it's a positive value already. K can't be negative. My y-intercept is equal to 1 over the initial concentration. Now the units for k for second order, it's molarity -1, S -1, so whatever your inverse concentration unit and your inverse time unit. And then finally, let's look at the y equals mx plus b format of this. So y is our 1 over the concentration at whatever time t. Our slope is just k, not negative k this time. Our t value, or x is our t value, and our y-intercept is 1 over the initial concentration. And that's called the integrated rate law. And it can help us track the changes over time. So you need to make sure for all three orders, the 0, first, and second order, you know what that graph looks like, which graph gives us a straight line, and how to find the rate constant k from the graph, and how to write the integrated rate law, so the y equals mx plus b format of that rate law. You should also know the units for k, but you needed to know that already. Okay, so half-life. Half-life is the amount of time it takes for half of the substance to react. And for doing nuclear chemistry, it's the time it takes for half of the sample to decay, to break down. Right. Nuclear half-life follows first-order kinetics. You can have half-life for any reaction. When you have half-life for first order, though, and this is important, first order, the half-life is constant. No matter how much you start out with, it will always take the same amount of time to break it in half. So there is an equation for first order half-life because it's constant, easy to use. So the half-life of the substance is going to be equal to 0.693 over k. Whatever the whatever the rate constant is for that reaction, you can plug that in for k. 0.693 divided by k will give you the amount of time it takes to break in half. So let me give you an example. If you start out with, I don't know, let's do a simple number to make it easy. Let's say we have 40 grams of a substance to begin with. After, let's say its half-life is 1 minute. Again, to make it simple. After 1 minute passes, I have 20 grams left. After another minute passes, I have 10 grams left. After another minute passes, I have 5 grams left. After another minute passes, I have 2.5 grams left. So each one of these cuts takes 1 minute. 1, 2, 3, 4 minutes. So it takes 4 minutes for 40 grams of that substance to decay into 2.5 grams. So that's kind of like the basis of half-life there. If you have a whole bunch of information, a quick check to see if it's first order is to see if the half-life is constant. So if you check your data and every like 5 minutes it breaks in half or something, and that's a consistent amount of time, you know it's first order. It's going to change if it's 0 order or second order. Okay, so here's an example. Using the data provided, determine the reaction order and calculate the value for k with units. Now, one strategy you can use is to graph it, and if so the time is always on the x-axis, concentration on the y-axis. If that's a straight line graph, then it's 0 order. And then you could take the natural log of each of these values. And if you get if the natural log of each of those values versus x, plot that. If that's a straight line, then it's first order. And if it's still not a straight line, then it's second order. We don't go past that for AP chemistry. But another strategy you could take, you don't have to graph, or if you don't have the capacity for graphing, then you could just kind of see what the change is for each of these. Because the change in time is consistent, we can see if the change in concentration is consistent. So I'm going to just subtract, and the difference here is 0.33. And then if I do it again, 0.9122 minus 0.6657, the change there is 0.2 0.624. I always check one more just to make sure. 0.6657 minus the 0.4858. Now the change is 0.17. So it is not changing by a consistent amount, so it is not zero order. And the next thing you could do is to figure out if it's first order. You could take the natural log of a couple of these values, okay, and then see if that changes consistently. Or you could see if the half-life time is consistent. So in this case, we don't see anything breaking down in half in terms of amount. Like if this was 0.625 here, that's half of 1.25, and you can see if then it breaks down even further into like 0.3125, but it doesn't follow that exact pattern, so I can't use half-life because they don't give us amounts cut in half. So let's go ahead and just take the natural log of some of these values. So let's do 1.25, natural log is 0.223, and then the natural log of 0.9122 is negative 0.092, and the natural log of 0.6657 is negative 0.407, and we'll do one more just to make sure. 0.4858, the natural log of that is negative 0.722. So now I want to see if that changes consistently. So you'll just subtract. And you get a difference here of 0.315. And you get a difference here of 0.315, and you get a difference here of 0.315. So now the difference between them is constant, and the difference in the time is constant, so you know that that must be a linear graph with the ln of the concentrations. Because the ln of concentration versus time is a straight line, we know it's first order. So that's our first bit of information. Then it says to calculate the value for K with units. Well, we know it's first order, so we can write a rate law. Rate equals K times A. We can also then, because it's first order, we know that we can use the integrated rate law. Is ln concentration at time t is equal to negative K t plus the ln of the initial concentration. So let's go ahead. I'm going to just use the natural log at time 100 because I have that as the negative 0.092 is equal to negative K. The t is 100. And then my initial concentration, or the ln of the initial concentration I already have, was 0.223. I can go ahead and solve for K. And I get 3.15 times 10 to the negative 3. And because it's first order, I know that the unit for the rate constant is the inverse time. But careful, this one, the time is in minutes, so it will be minutes negative 1 instead of seconds negative 1. Okay, so here's an example of a first order reaction with half-life. They tell you it's a first order reaction here. So anytime you encounter that in a question, I like to just circle it or underline it or something so I know, hey, they already told me the order of the reaction. Now, this one says it has 1/16 of the original amount left. It doesn't actually give you specific amounts. What I like to do is I like to use 100 then as my original amount. And we know that 1/16 of that, if we plug it in, 1/16 of that is 6.25 grams. Now there's kind of two approaches you could take to solve this. I'm going to show you the easy way first because these numbers are pretty simple. And then I'll show you the more chemistry way to do it. So because it's half-life, we're going to be cutting the sample in half. The amount of the sample cuts in half. So 100 cut in half, that's 50 grams. Cut in half, that's 25 grams. Cut in half, that's 12.5 grams. And cut in half again, that's 6.25. So it took 4 cuts, or 4 half-lives, in order to get it from 100 grams down to 6.25 grams. The total time then was 500 seconds. And we know for a first order reaction, each half-life is the same. Half-life is constant for first order. So I can divide that by 4 to get my half-life, which is 125 seconds. Okay, now let's say the numbers aren't as nice. You can still figure this out using the integrated rate law for a first order reaction. The integrated rate law for a first order reaction is the natural log of the concentration at time t is equal to negative kT plus the natural log of the initial concentration. So I know that my final concentration or final amount was 6.25 grams. Okay, and I know, well, I need to find the K after those 500 seconds have passed. And then I know my initial amount was 100. So if I plug that in, natural log of 6.25 minus the natural log of 100 divided by 500, and then I take the value for K is 0.00555, and the unit for K is inverse seconds because it's first order. From there, I can plug that into the half-life equation. Half-life for first order is 0.693 over K, and I know that my K value is 0.00555, and when I divide that, I get that the half-life is 125. So again, either way is fine. It just depends on the type of numbers that they give you.